Hi, in this video, we'll continue our journey into topology and introduce more notions that will help us build our understanding in real analysis. So, let's first define what a neighborhood is. So, in the previous video, I've defined that if X is in the closure, if and only if, for every open set containing X, it intersects A, the set A. And what does it mean to be an open set containing X? Well, we will rename it and call it a neighborhood. And while some mathematicians define neighborhoods differently as just a set that contains an open set containing X, then they define what our definition as open neighborhood. We shall stick to our definition because most of the time we anyway want to use the open set property instead of caring about the whole set. And so we shall call it open neighborhood for less confusion. So let's just take some examples. For example, X is the real line, then A is this half interval, A bar is this closed interval, because every neighborhood of 0 intersects A, while every point outside this has a neighborhood disjoint from A. And so with the idea of the neighborhood terminology now, we should define what is known as the limit point, or you can call it a cluster point or point of accumulation. But basically it is saying that if every neighborhood intersects A at some point other than X itself, then X is a limit point. So to say differently, X is a limit point if it belongs to the closure of A deleted the point X. The point X may lie in A or not, but for the definition, it doesn't matter. A good example is the one we have seen earlier. If A was the half closed interval 0 to 1, then 0 is a limit point. And any point inside this interval is a limit point. But outside the interval, then it is not a limit point, because there will exist a neighborhood outside that does not intersect A at any point other than itself. Another example will be the one over here, the set of 1 over n's as m runs through the positive integers. Then we can see that 0 is a limit point, because for every neighborhood you can find a 1 over n smaller than that delta neighborhood by the Archimedean property of the real numbers. If you don't recall what was the Archimedean property, you can watch my videos all the way from the start where I introduce the properties of the real numbers so that we can build our understanding from there. So, if you take a moment to realize, you can see that the closure of the set A is actually equal to the set A, and you add all its limit points inside. And the proof follows because if X is already in a limit point, then every neighborhood of X intersects A. Hence, it belongs to the closure by definition. And so, the set of limit points is a subset of the closure. And because of that, since A is also a subset of the closure of A by definition, it follows that the A union the limit points is a subset of the closure of A. And for the other side, we take a point in the closure. If it happens to lie in A, then it is true. And so suppose it doesn't lie in A, we want to show that it is a limit point. So X is an element of the closure, but X now is not an element of A. Since it's an element of the closure, we know that every neighborhood intersects A. And because X is not in A, it must intersect at that point different from X. Thus, X is an element of the limit points. X is a limit point. And so X is an element of A union with its limit points. And hence proving the reverse inclusion. And together this shows that the closure of A equals to A union the limit points. A corollary of this is saying that if a space is closed, if your set is closed, then A closure must equals to A. And because this equals to A union A, the limit points, it just means that the limit points is a subset of the A. Next, we shall prove that the supremum of a set always lies in its closure. And the proof also just follows because you're just proving that this supremum is a limit point. So, to prove that it is a limit point, you just need to prove that every neighborhood of this Y intersects E at a point different from itself. So, because for every H there exists a point X in between Y minus H and Y, and this X is in E, and this is because Y is the supremum, so Y minus H is not an upper bound. And we're done, because you can always find an X in between this neighborhood, in this neighborhood. Thus Y is a limit point, hence Y is in the closure. And what we want to now deal with is why we introduce the notion of this limit point. It sounds similar to the limits that we want to play with when we talk about convergence. So, in the real line, every 1 point set is closed. So, you can prove it yourself. But if you just take arbitrary topological space, then of course this 1 point set might not be closed because you can just define it to be open. And as a result of this, when you have like the following topology on this space, it could lead to convergence of a sequence into two values instead. So if you look at this example, the sequence defined by setting xn to equals to b converges not only to b, but also to the point A and C. And that's because we want to say that a point converges, a sequence converges to a point x if and only if every neighborhood of x there is a cutoff such that xn will eventually be all within the neighborhood itself. So in the real numbers, it cannot converge more than to 1 point. So the limit is unique. But in the arbitrary space, it can. Because if you use the definition that for every neighborhood there's a cutoff such that xn is an element of U, then for this example, you can see that for every neighborhood of A, it's either the whole set or this. And then you can see that the sequence B, it lies within it. And so A is also a limit, and C as well, while B is also a limit. And so you can see that in an arbitrary topological space, the limit of a sequence may not be unique. And so this causes a bit of confusion to many people, mathematicians. And so we need a property to ensure that the limit of a sequence is unique. And this property is known as a Hausdorff property, or more like when you say that a topological space is called a Hausdorff space, if for every pair x1, x2 that are distinct, there will exist open neighborhoods u1, u2 that are disjoint. So what is saying that if x1 and x2 are not equals to each other, then there exists u1 and u2 such that x1 is an element of u1, x2 is an element of u2, and u1 intersect u2 is empty. So, and a classic example will be just the discrete topology. Then X is Hausdorff. Because if you are given x1 and x2, then you can form the subsets of the singleton u1, u2 respectively. And then they are open because all subsets are open by the topology, but their intersection is empty. Also, if you are a metric space, then you are Hausdorff. And you can see why, because you can just take the radius to be the distance between x1 and x2, then take u1 to be the, so x1 is somewhere here, and then x2 is somewhere here, then the distance is r, so you take the midpoint, then you draw one circle here and one circle here. Then these two are both open sets because they are balls, and then their intersection is empty, and then you can just check this yourself. But I hope the picture is clear. So you've proven that all metric space is Hausdorff. So that means if you define a metric on the real number set, then it's Hausdorff. Or if you define it on complex number, it's Hausdorff. Euclidean space is Hausdorff. So you have a lot of Hausdorff spaces already. And then we now shall prove that in a Hausdorff space, your sequence can only converge to at most one point. So suppose that a sequence converges to X. If Y does not equal to X, then you can form disjoint neighborhoods of X and Y respectively. And since U contains Xn for all but finitely many values, V cannot. And so Y cannot be a limit. Or you can think of it as a contradiction proof. If your X and Y are both limits of a sequence, then at some cutoff, the xn's must lie all within U or all within V. But then they are disjoint. So that cannot happen. So you can take that or you can just follow this. Both should be clear to you. Hence, we can say that as xn converges, we can say x is the limit of the sequence xn. Some properties of Hausdorff, before we end the video, is that every finite point set in a Hausdorff space is closed. And we shall show this, it suffices to show that every one point set is closed. And so, we just need to show that X, the complement, is open. And so if X is a point different from X0, then X and X0 have disjoint open neighborhoods respectively. So U does not intersect X0, so the point X cannot belong to the closure of X0. And hence this means that no point is in the closure of X0, means the closure of X0 is X0 itself. So this one point set is closed as a result. So what does it mean? So let me repeat, what does it mean by does not intersect X0? Because they are disjoint, U intersect this neighborhood is empty for all X. So this means that none of the points are limit points. And so X0, the closure of, there's no limit points, meaning X closure equals to A union A prime, means this is just A, because A prime is empty. So since the closure equals to itself, it means that the one point set is closed. So there are many properties of Hausdorff space, such as a order topology on a set is going to be Hausdorff. The product of two Hausdorff spaces are Hausdorff, and the subspace of a Hausdorff space is Hausdorff. So you can see Hausdorff space are very, very nice to use because it has many properties. And the proof of the order topology and product, I'll leave it to you. I'll prove the subspace one, and you should have a feel of how to use the property of a Hausdorffness to help prove other properties. So let A be a subset of X, where X is Hausdorff. So you want to prove A is Hausdorff. So you just take 2 points A, you want to prove that you can find open sets disjoint from each other. So because x1 and x2 are in A, they are also in X. And as a result of the Hausdorff norm, you can find U1, U2, U and V open in X such that their intersection is empty. Then you just take U intersect A and V intersect A. And this will be open in A by the definition of the subspace topology. And then U intersect A intersect V intersect A must be empty because U and V are disjoint. Hence A is Hausdorff. And so you can see as we journey along now how analysis comes into play, as now we have talked about convergence of sequences and the role it plays having the Hausdorff property to talk about the limit. I've come to the end of this video. Please like, share and subscribe, and I'll catch you in the next one. Bye!